All right, let's get going. So, as I was telling these guys, Zusi, Annie, if you have any questions, because I know lots of people, aside from Manny, have an upcoming midterm. Manny already had his. So if you have any questions about the practice midterms that have been posted, you're welcome to ask them. I was going to talk about more volume stuff today, but if there are things from any of these practice midterms that you want me to look at, I have them all printed out here. So you could certainly ask me to cover something from that, and I'd be happy to. If you don't, I'm just going to go ahead and start talking about volume. The rhythm, I guess you should ask, is there anything from Hunter's practice midterm that you want me to?
Can we do it like by the end?
Sure, yeah.
Yeah.
Okay. All right. Yeah, so more volume stuff. Yeah, okay, sure. We talked about that. Sorry, one second. Let me just make sure I'm in the right spot here. We did that, okay. Cool. So the thing to know about volumes of revolution is there's kind of two ways you can go. So let's cover this example. Yeah. Let's do this. So let's say we're going to use the following region. So the region bounded by y equal to x squared and y equal to 3x. And we're going to set up a bunch of different angles. I'm going to close that door. So that's our region. And we're going to revolve it around a bunch of different axes. So first, we're going to revolve it around the x-axis. And so we don't have to draw the region, but I find it useful to draw the region. So we're looking at something that is, right, y equals x squared, y equals 3x. So y equals 3x looks something like this. And y equals x squared looks something like this. And of course, there's more to it than just that, but that's the portion we want. We can see that they intersect at 0, 0, and you can either set these equal to each other and then bring everything to the left and factor to get x equals 0 and x equals 3. Come on in. Or you can probably just guess a little. So if we're going around the x-axis, we need a vertical strip. Right, so with the washer or disk method, the strip is always going to be perpendicular to the axis of rotation. Since we're going around the x-axis, our strip has to be vertical. I don't really like drawing the shape. I don't find the actual like volume thing to be particularly useful, but I do like drawing what this looks like when I revolve it around. So if I revolve this around, it's going to look like this. Let's give myself a little more room here. Again, right? I mean, it'll look kind of like that. Now, really, you don't have to do any of these drawings, right? You could totally not draw this at all. I do think we need the region to help us figure out what's going on. But other than the region, I don't think you really need anything else. The volume of this washer is pi times the big radius squared minus the little radius squared times the thickness. All right, that thickness is just a small change in x. The big radius here, extend this outwards here, right? Here's my big radius, which is just the function that's further away from the axis of rotation. My small radius is the function that's closer to the axis of rotation. That's going to be y equal to x squared. Specifically, the 3x and the x squared.
Why couldn't we define a radius of the top minus the bottom and go take that?
Because if you did that, it's a totally different thing. So the thing is, right, if you're trying to find, so let me just point out, if you're trying to find the area of this big circle minus this little circle, right? So let's say you have a circle, I'm just going to draw a picture here. Let's say we have a circle of radius 4, and inside we have a circle of radius 1, right? And the area of the difference here, that washer, that area is going to be pi times 4 squared minus pi times 1 squared. And that's definitely 15 pi. And that's definitely not pi times 4 minus 1 squared. It's not. 4 minus 1 is 3. 3 squared is 9. Those are not the same. So with subtracting 2 radii and then squaring it versus squaring the radii and then subtracting them results in a totally different thing.
The first one results in the washer that you're looking for. What is the second one saying? Is it saying that particular radius 3?
Yeah, it's a radius of 3, exactly.
It's not that shape.
Right, exactly. It's just a circle with the radius that is the difference of these two functions, and it's not going to give you the same area.
So pretty much never we're gonna see that as our radius.
That's exactly correct.
Okay,
Yeah.
that makes sense now.
Yeah.
If you draw it and you're still not sure which one's bigger or smaller, you just plug in the number.
So if I do this, I want to go from bigger to smaller. I know that my endpoints are 0, 0 to 3, 9. So I could plug in any x value between 0 and 3, like x equal to 1. And I see that 1 squared is 1 and 3 times 1 is 3. So the 3x function is the bigger function. So then my total volume is going to equal pi times the integral from x equals 0 to x equals 3 of my big radius, which was 3x squared, minus my little radius, which was x squared. And although usually a lot of people will just have you set these up because going further is kind of pain, but this one isn't too hard to simplify, right? We could totally figure this out and get pi times, let's see, the integral from 0 to 3 of 9x squared minus x to the 4th. We integrate, we get pi times 9x cubed over 3 minus x to the 5th over 5. From 0 to 3, we plug in, we get pi times 9 times 27 over 3. I could have canceled the 3, I guess, minus 3 to the 5th over 5. I wouldn't bother too much with simplifying this anymore. You certainly could if you wanted to. I guess I could do one thing. That's pi times 9 over 3 is 3, and 3 times 27 is 81, minus 3 to the 5th over 5. So the point really is just that we can evaluate this without too much effort here. Let's see. Yeah, I think that's good. Okay. So we're going to take the same region like 5 more times and rotate it around different axes to kind of see what happens. So let's go around. Let's continue in the x direction because I think that's a good idea. Meaning, let's revolve around now. Let's make my life a little bit easier. So I can draw this picture. Let's revolve the same shape around the axis y equal to -2. So same shape. Doesn't need to be perfect. And now my axis is down here, y equal to -2. Still having the same sort of strip, still using a vertical strip that's perpendicular to my axis of rotation. But now my radii are going to be a little bit different. So what I should have been saying this whole time is this, in this previous problem here, the outer radius is really 3x minus 0. Because it's the difference between my function and my axis of rotation, which is the line y equals 0. And my inner radius was x squared minus 0. Here, my outer radius is going to be my further away function, which is 3x minus -2. And my inner radius is going to be x squared minus -2. And sadly, the -2's won't just cancel each other out. Because if we're going to find the volume of our washer, just like every time we use the washer method, it's going to be pi times your big radius squared minus your little radius squared times your thickness, which in this case is dx. Okay, well, in this particular case, it's going to be gross. We're definitely not going to evaluate this one. It's going to be pi times your big radius is 3x minus -2. Let's write +2 squared. And your little radius is x squared plus 2 squared. And certainly if you multiply all this out, some stuff will cancel, but the twos just don't cancel straight away. Then your total volume is going to be still the integral from 0 to 3. When I think about my limits of integration, I think about if I have a vertical strip, how far left in the region it can move and how far right in the region it can move. So it can go as far left as 0 and as far right as 3. Right? I mean, it's gonna be really tiny when it's up here, but you know, that's kind of the idea. It can slide left and right through the region. So our total volume is going to be pi times the integral from 0 to 3 of this gross mess. 3x plus 2 squared minus x squared plus 2 squared dx. And then to evaluate it, you would just multiply everything. So I'll just show you one more step because I don't want to do any more than that. But this would be 9x squared plus 12x plus 4 minus x to the 4th plus 4x squared plus 4. And then you subtract and then you integrate and then you plug in and be gross.
So if we didn't know which one was the higher, we didn't want to actually plug in numbers, and let's say we did all the calculations, got negative value, could we just flip the sign? Is it true the same way for area?
It should be, yes, too. I'm assuming you're saying specifically that you got these parts interchanged. Yeah.
If you get it wrong, just get
Yeah.
negative value.
Now it is this is actually not that important. I want to say it's important, but it's really not, right? Technically, when you're finding the inner radius or the outer radius, you can really subtract in either direction here, because whether you do the function minus the axis or the axis minus the function, you're going to end up squaring it, and so it'll still end up being positive either way. But the reason it's going to be consistent here is because when we start talking about the shell method, we do have to pay special attention to the order of subtraction. So it's just good to do it the right way from the beginning so that we don't make any dumb mistakes later on. Okay, let's do one more around the horizontal line. Let's revolve around y equal to 10. Typically, when you're doing volumes of revolution, you should not be revolving through the region itself, meaning typically your axis of rotation should be outside of the region. I saw one person who had a homework problem the other day where it was kind of like it was revolving onto itself, and it was usually not something we deal with in this class. So I would say try not to worry about that. Okay, yep, sure. So same region. Draw my nice little picture here. And now my axis of rotation is up here. So if I draw my little strip, now my outer radius is 10 minus the function that's further away from it, which is x squared. And my inner radius is 10 minus 3x. So the outer radius is always the difference between the function that's further away and your axis of rotation. And the inner radius is always the difference between the function that's closer and your axis of rotation. And when I say difference, I just mean subtract, because that's how we find the difference. So here, one more time, the volume of my washer is going to be pi times big R squared minus little r squared times the thickness. I like to write that every time. Like I just find it comforting. It's like, oh yeah, I remember what I'm doing. So then we would have the volume of our washer would be pi times the big radius is 10 minus x squared minus the little radius is 10 minus 3x squared dx. And then finally, to find the volume, we would just integrate that from 0 to 3. Put the pi out in front because we can. Yeah. So what I'll say is technically it doesn't matter, because either way, whether the 10 minus x squared or the x squared minus 10 is positive or negative, since we end up squaring it, it doesn't matter, it's going to be positive in the end. But the reason I'm subtracting 10 minus x squared is because 10 is the larger value and x squared is the smaller value. Right? Like if you're between 0 and 3 for x, right? Like if you're 2 squared is 4, and that's definitely smaller than 10. But I'm really just looking at the graph and seeing that 10 is higher up, so I know I'm going to do 10 minus the lower function. Right, so that's why here we did the function minus the axis, and here we're doing the axis minus the function, because here the functions were bigger, and here the axis is bigger.
So if you could function that's very difficult to actually draw, let's say it's not a polynomial,
Sure,
it's like e times sine, some crazy function.
sure.
How could we, do we need to visualize that?
Yeah, it's usually to your benefit to visualize it. So what I would say is, one, typically if you're doing volumes revolution, they're not usually giving you things that are too terrible to draw. Two, on a not exam, you could use Desmos to visualize the thing. In your class, you're definitely not going to see anything terrible. Sure, 100% confident. So yeah. So let's see what happens if we revolve around the y-axis now, or other vertical axes. So same region, we got 3 more to go here. There's my region. And now we're going around the y-axis. So what I'll point out is that as soon as we talk about the shell method, it's going to be true that you can use, usually with some exceptions, any method you want. And the deciding kind of piece of information is really, what kind of strip do you want to draw? Is it more beneficial to draw a vertical strip, or is it more beneficial to draw a horizontal strip? If you want to draw a horizontal strip and it's perpendicular to your axis, then you know you're going to be using the disc or washer method. Really, you should be thinking of the disc washer method as the same method. A disc washer, same thing. The only difference is the disc method, you just don't have the inner thing that you're subtracting out. The shell method, on the other hand, is totally different. In the shell method, your strips will be parallel to the axis of rotation. And that's really the differentiating factor there. Shell is parallel, disc washer is perpendicular. Okay, so same idea. We're going to say that the volume of our washer is just going to be pi times your big radius squared minus your little radius squared times dy this time, because it's the thickness is now dy. Okay. So I could draw this one. I could draw it one time. I bring this down. I try to draw my inner circle and then my outer circle, and then give it a little bit of thickness, and then give it a little bit of depth. There we go. There's my washer. And the volume of this washer is definitely, well, my big radius is the right function minus the left function, which is 0. Sorry, I mean, minus the axis of rotation, which is 0. Sorry. So my right function here was y equal to x squared, but we have to write x as a function of y. So that's going to become x equal to the positive square root of y, because we're on the right side. And my small radius, which I didn't give myself enough room for here. Good call, James. Do that fine like that. My small radius is the inner function minus 0. So that's going to be, well, again, my inner function was y equal to 3x. And now I need x equal to y over 3. That's going to be my inner radius. And then it's the same deal every time for the washer method. My washer is going to have a volume of pi times square root of y squared minus y over 3 squared dy. And then my total volume is going to be pi times the integral from 0 to 9, as we're asking now what the y values are, how low the lowest y value is 0, how high the highest y value is 9, of the same thing. Square root of y squared minus y over 3 squared. Yes, we could integrate. I mean, any of them we could do. It's just how much arithmetic do you feel like doing?
Question in the textbook, it was in the context of shell method,
Right.
but it was similar to this one.
Sure.
The only difference was we were trying to integrate with respect to the y-axis because we wanted to do the x, we are rotate by the x-axis,
Sure.
but the point of intersection was -1. So the
Okay.
same shape, but it was y equals x plus two, so the point of intersection was negative.
Okay,
1.
sure, yeah, okay.
But then for that, the only way to get it with the shell method was actually putting two integrations. So the top part minus the bottom part, because the bottom part is not defined.
Oh,
by-
did your region look something kind of like this? Was it kind of more like,
Yeah, exactly.
yeah, right, so definitely you could do this using shell or you could use this using washer. And in my opinion, I mean, depending on the expectation, this region is better to attack using a vertical strip. Because a vertical strip is always going to have the same top function and the same bottom function. Now, if we're specifically being told we have to use a certain method with a certain axis, then we don't have any choice. And you would have to break it up into two intervals.
So for example, for this one, if it's the bottom is 0, you would take not the shell method, but the one get the.
So you're saying like the axis of rotation, maybe it's like this, for example, just to kind of pretend like we know what it is. Like that.
Something like that.
And so then,
But this was on the negative side, that was the problem. So the half side before 0 was on the negative side. So function was not defined on that area because the square root of y is not defined. Because y equals x squared.
Sure.
And you turn it into
right,
x,
yeah, so y equals x squared, the right half is x equal to the square root of y, and the left half is x equal to the negative square root of y.
Is there any way of attacking this without having to go through that?
No, definitely not. Not if you want to do it that way. If you want to use horizontal strips, you have to break it up like that.
But vertical strips, you can just take the bigger radius minus the small radius, right?
Exactly. Well, the bigger radius squared minus the
Minus
small
the
radius
square.
squared. Yeah, we'll come back to something like this in hopefully today, maybe. Let's see. All right, so yeah. So then just to kind of piggyback on the same ideas, if we want to go around, say the line x equal to 5, then it's gonna be the same sort of region, but now rotated around this axis here. So now if we're using horizontal strips again, well, here is my outer radius. Here is my inner radius. So the volume of my washer here, one more time, pi times big radius squared minus little radius squared dy. My big radius is 5 minus the function that's further away. So my, whoa, that's interesting, okay. So it's going to be 5 minus that function there, which was y over 3. Minus my small radius is going to be 5 minus the closer function, which is square root of y. By the way, when I'm doing this, when I have a different axis of rotation, I'm really thinking of this as, oh, that's the line x equals 5. So I should be subtracting x equal to something else. X equals 5 minus x equals y over 3. X equals 5 minus x equals root y. That's the way I kind of keep it straight in my head. Also, I know the dy there means things have to be functions of y. Right? You can't have x's. So then my total volume would be, one more time, pi integral 0 to 9, all this jazz. Not fun to calculate, but not impossible to calculate, just a royal pain in the ass. All right, and then lastly, if we went around something like x equal to -2, same idea, except now the outer one's going to be this one and the inner one's going to be this one. So yeah, might as well write it, could be complete. So if we go around x equal to -2. So now here is my horizontal strip. And here is my inner radius. And there's my outer radius. The inner radius is right minus left. So it's going to be my y over 3 minus my -2. And my outer radius is going to be also right minus left, which will be square root of y minus -2. Then the volume of my washer, as usual, pi big R squared minus little r squared dy. I feel like we've all heard it enough times now that we can never forget it, right? Volume of washer, pi times big R squared minus little r squared times the thickness. And so in this case, it's going to be pi times. I would take the step of simplifying this one part, but this is going to be square root of y plus 2 squared minus y over 3 plus 2 squared dy. And then finally, the total volume would be the integral pi times integral from 0 to 9, once again, square root of y plus 2 squared minus y over 3 plus 2 squared. These kind of shapes start to look kind of funky. Like I'll just point out, right? If you rotate this kind of thing around an axis over here, it kind of looks like this picture here, right? You've got that shape just kind of rotated around. I know it's a different example, but I just noticed the picture looked the same, so I just thought I would grab it. That's kind of nice. That's kind of what's happening. You're just kind of spreading out your axis of rotation or making your radii further longer. Further longer? Yeah, further longer. Definitely further longer. So let's get to the fun stuff. What if I want to find the volume? We're actually going to find it this time of the region. Maybe we'll find it. Yeah, we will. Bounded by. This is one of my favorite regions. I'll be honest. Y equal to 0. F of x equal to 6 minus x, and g of x equal to the square root of x. Revolved around the y-axis. Something to note here. The y-axis is my axis of revolution. And I wrote the wrong thing here. I meant to write x equals 0. Sorry. This should have been x equals 0, not y equals 0. I want that region here. Sorry. So the y-axis is my axis of revolution, and the y-axis, x equals 0, is one of my boundaries. So when one of your boundaries is the axis of rotation, you're not missing anything. You don't have that inner circle to subtract it. Or in other words, when your axis of revolution is one of your boundaries, you're going to be using the disk, not the washer method. The region looks, I'm just going to draw the region. It looks like this. We get to the point 4, 2. Sure. So this is the point 4, 2. To the point 0, 6, 0, 0. And right, there's my whole region. All right, and this square root function would continue on that way, and this line would continue down that way, but I just want the region bounded by those two things. Okay, so if I'm rotating around the y-axis, what kind of strips do I have to use? Horizontal. Well, so I phrased it in a way that was a little ambiguous. I should say, based on the fact that we only know how to do the disk and washer method currently, and we're rotating around a vertical axis, what kind of strips do we have to use? Horizontal, because they have to be perpendicular to the axis of rotation. The problem, or the unfortunate thing about that, is we have to break this up, right? This strip and this strip have different right-hand functions. So if we rotate this thing around, let's see if I can do a decent job drawing this. Maybe not. Kind of cool looking. So right up here, we have discs that look like this. And down here, we have discs that look like this. So the volume of that disk is pi times the radius squared times the thickness, which is dy. And the radius is, well, that function is y equals 6 minus x, which becomes x equals 6 minus y. That's my radius. Whereas down here, below this kind of breaking point, the volume of this disk is also pi times the radius squared dy. But this radius, well, that function is y equal to the square root of x, or x equal to y squared. So that's going to be pi times y squared dy. If I wanted to find the volume of this whole thing, I have to do two integrals. I have to do the integral from 0 to 2 of this lower shape, which is using this lower function. So that's going to be the pi times y squared dy plus the integral from 2 to 6. But now my radius is the other function, 6 minus y squared. So pi times 6 minus y squared dy. And typically people think of this as bad. We don't want to do two integrals if we don't absolutely have to. And we don't absolutely have to if we do this using a different method. I mean, it's not really bad, but like people are like, oh, why are you using two integrals when you use one? So, sorry. Alternatively, we can do something else. And I said we were fine. I said we were going to do this. Do we really want to do it? We will, yes. That's going to be pi times the integral of y. I guess I should write it out. Fine. Sorry, here's the work if you really want it. I suppose I could completely factor out the pi. That's going to be 36 minus 12y plus y squared dy. This is why it's good to be good at algebra, because like algebra does come up. You have to actually do algebra sometimes. That's going to be pi times y to the 5th over 5 from 0 to 2 plus, oh my God, 36y minus 12y squared over 2 plus y cubed over 3 from 2 to 6. No one wants to do that. So we're going to get pi times 32 over 5 plus a whole bunch of garbage. 36 times 6 is 216 minus 6 times 36 is 216 plus 6 cubed is 216 over 3. Minus plug in 2, you get 36 times 2, which is 72, minus 6 times 4, which is 24, plus 8/3. And that's a number. Great. Done. Or you could do the shell method. So take the same region. And use a vertical strip. A strip that is parallel to the axis of rotation. So we can use the shell method. And I do encourage you to remember our shell method where our strip is parallel. And even though it's a bit of a stretch, parallel rhymes with shell. It works. That's how I remembered it for literally 20 some years. So shell rhymes with parallel. So your strip is parallel to your axis of rotation. You're using the shell method. Great. So here's why it's called the shell method. Because when you rotate this thing around, if I can draw this decently. You're getting a shell of a cylinder. You're getting this shape here. Right, is a cylinder, but it's got a little bit of thickness to it. That's the idea. And so to find the volume of the shell, it's a totally different formula. It's not pi times big R squared minus little r squared. It's, well, here's what I like to think of. There's a couple different ways of actually deriving this formula, but here's the way that I think makes the most sense. Essentially, this is a very thin piece of paper, or a piece of paper with a little bit of thickness, And yeah, technically, if you unrolled this, the inner circumference is a little smaller than the outer circumference. We're gonna ignore that. So let's say we took this shape, this cylindrical shell. Wow, that's a decently not great drawing. And what we're going to do is we're going to unroll it. We're going to cut it right here. And then we're going to unroll it. And when you do that, you get something that's kind of like this. Here's this part here. And the volume of this shape, well, if we say that the height here is h, and if this cylinder had a radius of r, then this rectangular parallelepiped has a length of the circumference, which is 2 pi r. And then the thickness is a little change in x. So the volume here of our shell is 2 pi r times h times the thickness. Now, importantly, and this is where things feel very, very different. In the disk washer method, the radius is the function. Typically, right? Like however far the function is from the axis of rotation, that's your radius. In the shell method, the radius is not the function. In the shell method, the radius is how far you are from the axis of rotation. So great, I've gone some distance, let's call it x from the axis of rotation. Or if I'm going this way, y. So basically, if you're revolving around the y-axis, your radius is going to be x. And your height of your shell is going to be the top function minus the bottom function. Which I thought I gave these better names somewhere. You write this down real quick, which in this particular case, when I call them f of x and g of x, right? If I'm calling this f of x and this g of x, it's just f of x minus g of x. See, Manny? So that's how the shell method is typically set up. It's 2 pi times whichever variable you're using, x if you're doing dx, y if you're doing dy, and then times the difference, the height of the function, so the top function minus the bottom function. So here, that's going to be 2 pi x times 6 minus x minus the square root of x. And so then the total volume, which I wish I had left more over there, but the total volume is just going to be, we're going to add up all the shells. So, right, so we have some really skinny shells and some fatter shells. Our radius, our x is going to go from 0 all the way out to whatever the x value is here, which was 4. So our total volume is going to be the integral from 0 to 4. Usually we put the 2 pi out in front and say it's 2 pi times x times 6 minus x minus the square root of x. Yes. There's your radius. There's your height. Yeah.
So if we're not given a value for x, does it just stay as a variable?
It's never going to be given a value, because here's the idea. So let's go back over here for a second. Right, the whole idea is this is just a representative slice. Right, really, there's a bunch of washers or discs, right, that we're adding up. Right, and there's some good pictures in your book. Look at the pictures in your book because you paid a lot for the book, and you might as well use it for something. And the pictures are nice. But they show like these things where you've like got a bunch of just slices that are smaller and smaller and smaller stacked on top of each other. Well, the same idea is true over here. We're going to be letting the radius of the shell vary from really tiny. So when I've got a really tiny radius, here is my shell. Right? And then I let the radius get a little bit bigger. So now here's my new shell. Right, the radius is getting bigger as x moves further to the right.
So when we evaluate that, an answer is gonna have like
Totally, yeah. And so what I want to point out though is these really do, they don't so much stack as surround each other, right? You've got like the fattest shell out here, but it's just a shell, right? It's not the whole disk, it's really just this little shell's worth out here. No, Boris, yeah, you're good. So we've got this big shell, and then smaller shell, and then smaller shell, and then smaller shell, and then smaller shell, and we're just adding all up the volume for the shells. Question: what happens to the dx and the volume of the shell formula? So the dx is there, right? So it's right here, right? So there's dx, that's your thickness of this shell. And then so you've got thickness times circumference or length of the rectangle times height, which is difference in the functions.
on the third, after it says B shell, 2 lines down. Do you mean?
Oh, that, Susie, if that's what you're asking about, yeah, I just missed it there. Sorry. Yeah, good call, good catch. Cool. So. Since we've already talked, that's a pretty good picture. Usually my pictures kind of suck. That was not half bad.
Professional.
Thanks. So let's talk about what happens if your axis of rotation is a tiny bit different. So let's say instead, what if same region revolved around, that'd be super weird looking, x equal to -2. So, but I really should point out the distance, right, this is the radius, right? The distance from your strip to your axis of rotation. And since the strip and the axis of rotation are parallel to each other, that distance is always, for some particular value, always the same, right? It's not like you're moving further or closer, right? This strip that is x away from the axis of rotation is always x, no matter how high or low you go. Because it's not like moving to the right. Okay, so let's do the same region, but now revolved around x equals -2. So I might not draw it, we'll see. I mean, I'll draw the region first. But now we're going around. X equal to -2. So I'm still going to draw a shell. Or a strip, I should say. And I guess I could imagine, right, if I were to rotate the strip around, well, now this is my radius. So if I try and double this up here. I don't really want to draw the whole shape, but here is the shell. So there's your shell. And notably, the only difference between this shell and the previous first shell we drew is that it's got a bigger radius. It's still got the same height, right? Assuming I've drawn the dx like at the same spot, right? This height here and this height here are the same. So the volume is still going to be 2 times pi times the radius times the height. It's just that the radius got bigger. How much bigger did the radius get? Well, how far did I move my axis of rotation? 2. My radius is 2 bigger. Now, here's the easier way to do it. This strip is located at x. We have moved it x to the right. And we specifically want to say just x, because x can be any number that's in our limits of integration. So this strip is x to the right. Okay, so if this strip is located at x, how far is it from x equal to -2? Well, say again? Right. Well, I'm in x is slightly different, but you're totally right. So the distance from the vertical strip to the axis of rotation is, well, the way we find the distance between any two things is we subtract them. So it's going to be the radius is x minus 2. Now, I should point out, but I'm not actually going to do it. If we were to have done a axis of rotation over here to the right instead, then it would have been our axis minus x. And there the order would matter because we're not squaring something away and turning a negative into a positive if we get it wrong.
So if it was that,
6, right. So yeah, in fact. Sure. Right, if instead we were doing this around x equals 6, we were using a vertical strip. First of all, it looks super funky, right? I can kind of imagine revolving this shape around that axis and getting, something that's like, like this, like that, kind of, right? Like you can kind of see that maybe what that would kind of look like, some weird, like bizarre cylinder thing that has like pointy, I don't know, it's,
like an arrow.
yeah, kind of like an arrow, like an arrowhead maybe. And the shaft would go through that point. That's a good, I like your description. That's an excellent description. Whereas here, if we revolve around this one, then it's looking super funky, like, I don't know, right? Like that. Right? I don't know what the heck that is. It's weird. It's some cylinder with bizarreness cut out of the middle. Anyway, the point is that here, if we were doing the same sort of thing, the radius would be not x minus 6, but 6 minus x. Because x is smaller than 6 in this case. Anyway, back to this one here. The radius is x plus 2. So then the volume of our shell is 2 pi times the radius times the height. Where the radius, what I miss, Lucy? That you wrote down before? The dx, the thickness. You always need to multiply by the thickness. You got a thickness for the thickness. All right, so multiply by the r, which is going to be x plus 2, and the height, which is the same as before. Top function minus bottom function. That's going to be x plus 6 minus square root of x. And then finally, the total volume is just going to be 2 pi times the integral of x plus 2 times this gross x plus 6 minus square root of x. It does start to get really gnarly when you have different axes of rotation, which is why most of the time, at least on exams, you'll only see volume questions where you revolve. So I said, on exams, typically you'll see easy volume questions where you revolve around either the x or the y axis and have to calculate something not too terrible, or really terrible volume questions where they are only asking you to set up the integral and not evaluate it. Now, I don't think is volume going to be on either of your exams?
We haven't covered.
Okay, so probably not, but you, yes, okay. So just, whenever you see volume either on your first or second exam, be aware that there's probably going to be some where they make you calculate it and it shouldn't be too terrible, but there will almost definitely be ones where you have to set it up and it's kind of shitty, but you don't actually have to calculate it. Right, exactly. We would stop right here, and you don't want to do any. Oh, sorry. One more thing. We do need the limits of integration, which are from x equals 0 to x equals 4.
So the limits of integration, they don't include the axis at all.
Right. The limits of integration should only be describing the region before you've even thought about rotating it. That's why I like drawing. That's why I do think it's good to draw the region even and not necessarily draw the rotation, because the region is that x goes from 0 to 4. And I do think it's also worth mentioning that when you see a dx here, it's going to be x equals something to x equals something. If you see a dy here, it's going to be y equals something to y equals something. And I guess we should stop there because it's 2 o'clock. Next time we'll talk about doing a shell method with going around the x-axis, meaning you would have to be in terms of y. So basically, once you've decided what kind of strip you want, if it's a vertical strip and you're going around the y-axis, you have to use parallel, or you have to use shell, because you're stripping your axis of parallel. If it's a vertical strip and you're going around the x-axis, you have to use disk or washer method. If it's a horizontal strip and you're going around the x-axis, you have to use shell. If it's a horizontal strip and you're going around the y-axis, you have to use disc or washer method. So disc and washer, the difference is this sort of region around either axis, but specifically on the x-axis, you have to use washer. Whereas this sort of region around the x-axis, you can use disc. Because this is flush with the axis of rotation and this is not. Here, when you draw your little strip, right, and you rotate it, you're gonna get stuff missing in the middle. Right, whereas here, so basically, when you draw your strip, if it's touching the axis of rotation, it's gonna be disc, and if it's not, it's gonna be washer. Yeah, that's a good way to think about it. All right, I should stop because they're